So for our, the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Yeah, even if they've never seen before, we're confident that they could see. And then the other application being in the motor cortex, where we would initially enable someone who has no ability, almost no ability to operate their muscles, sort of like a sort of Stephen Hawking type situation, and enable them to operate their phone faster than someone who has working hands. But then obviously even better than that would be to bridge the connection. Take the signals from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to Neuralink devices located in the spinal cord. So we're confident there are no physical limitations to enabling full body functionality. I mean, as miraculous as it may sound, we're confident that it is possible to restore full body functionality to someone who has a severed spinal cord. So, yeah.
I was inspired to join this company because I saw in our device the potential to restore vision to people rendered blind by eye injury or disease. There are a number of particular characteristics of our device that make it uniquely suited to this application. Firstly, as well as being able to record from every channel, we can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. Secondly, our device can have an enormous number of electrodes. For a visual prosthesis, this is important because the more electrodes you can have, the higher density of an image you can create in the brain. Thirdly, thanks to our robot, we can insert these electrodes deeply into the brain. Now, this is an important thing for a visual prosthesis because the human visual cortex is buried deeply in a fold in the medial face of the brain called the calcarine sulcus. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. And if you unfold it and flatten it, you see that the image is inverted, it's upside down. But more interestingly, it's distorted so that the central part of the visual field, the fixation point, is greatly magnified. So for example, if you look at this image of Lincoln, if you look directly into his right eye, everything to the left of that fixation point is directed to your right visual cortex, and everything to the right goes to your left visual cortex. His eye, even though it's very small in the image, is magnified in the brain to occupy nearly a quarter of the surface area of the visual cortex. Over the last half century, visual neuroscientists have developed a profound understanding of visual processing in the brain. What's driven most of this research is recording from single cells in the cortex, usually of macaque monkeys. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. Another location in visual cortex will have a location elsewhere on the screen, in this case in the lower visual field. These regions are called receptive fields. We've inserted our device into the visual cortex of 2 rhesus monkeys, whose names are Code and Dash. That means we can record activity from their visual cortex generated by their normal home environment as they roam around. But as we all know, monkeys love banana smoothie. That means we can easily teach them to fixate points on a screen and reward them. We can reward them very precisely because we can track the location of their eye using an infrared camera. One of the things this allows us to do is to plot the receptive fields for every neuron that we can record with a single device. Now we do this by showing the animal a movie of random checkerboards whilst he fixates steadily on the screen. Then we take only the frames of the movie that generated a response in the cell and average them all together. This is a technique known as reverse correlation. It's generally used quite widely in visual neuroscience for this purpose. And this is an example of a receptive field plotted with this technique. The central cross is the fixation point, and you can see the little red and blue regions of excitatory and inhibitory receptive field. These regions give cortical cells some of their characteristic properties. So we can record all the receptive fields from all the electrodes at the same time. And if we take all these receptive fields and accumulate them together, overlap them, and place them on a computer monitor for scale at a typical viewing distance, you begin to get an idea of how much of the visual field we can cover with this preliminary device. Many of the receptive fields are close to the fovea, close to the fixation point. That's partly due to the magnification that I talked about of the fovea. But there's also a scattering of fields in the periphery. These are from recording sites deeper in the brain, in the calcarine sulcus. So far, I've only talked about recording information from the cortex. But to produce a visual prosthesis, we need to stimulate. So, if we stimulated the cells whose receptive fields are in this location, we would produce a perception of a flash in that location that only the monkey can see. How do we know that the monkey sees it? How do we know what it looks like? Well, unfortunately, we can't ask them what they see, but we can train them to tell us something about that phosphene. We start by training the monkey to fixate a central point on the screen, like this white dot, and we start by presenting real visual stimuli on the screen and rewarding the monkey for making eye movements toward those stimuli. So here we flash a white dot, and the monkey makes an eye movement towards it, symbolized by the green arrow. We then choose another random location and reward the monkey for making an eye movement towards it. Once he's got good at this task, we can begin to interleave these real stimuli with electrical stimulation of electrodes and produce a phosphene. The monkey sees the flash and naturally makes a saccade towards it. This tells us not only where in the visual field the flash occurred, but we can also change the current that we inject in that electrode to see how often he makes that saccade, how noticeable or how big perhaps the stimulation, the phosphene is that we're producing. Let's look at Code performing this task. I want to show you first at 1/4 speed. There's a visual flash, and he makes an eye movement towards it. The monkey can only see what is white on this screen. He can't see his own eye movement, and he certainly can't see when we stimulate. But here we stimulate, and he makes the same saccade to the same location because we stimulated the same electrode. Nothing appears on the screen at that time, and he has no other cue to make that eye movement. Let me show you this in real time. You can see monkeys like to work very quickly. And when we stimulate, he makes that saccade in real time. And looks like he's had enough. So what I've shown you is a way to produce a phosphene in the visual field. This is not something new in visual neuroscience, but if you think about that phosphene as a single pixel in a visual image, all we need to do is scale up and produce a great many more pixels and have them covering the visual field. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right. But as Avinash told you, our next generation of the device will have 16,000 electrodes. If you put a device on both sides of your visual cortex, that would give you 32,000 points of light to make an image in someone who's blind. Our goal will be to turn the lights on for someone who's spent decades living in the dark.
My name is Joey. I'm a neuroengineer, and I'm the head for the next-gen team at Neuralink. So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the N1 link as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. First, a little neuroanatomy. Movement intentions arise in motor cortex and are sent down long nerve fibers through the spinal cord. These are upper motor neurons. In the spinal cord, they synapse, that is, make a connection with another motor neuron, a lower motor neuron, which sends these movement intentions to the muscles, which contract, and in turn you have movement. While of course there are many other circuits involved in voluntary movement, you can think about the spinal cord as many pairs of these two connections. And in spinal cord injury, one of these connections is severed, unable to make the muscles contract. Let's zoom a little bit further. So here you can see on the left a cross-section of the spinal cord with a fiber coming down schematically. This travels through the white matter tracts. This is the upper motor neuron. And then it synapses within this butterfly-shaped region of gray matter in what's known as a motor pool. In the motor pool, the lower motor neuron descends out the ventral roots to the muscles, which contract. And then the sensory consequences of those movements, for example, the touch of your hand against an object, return to the spinal cord through the dorsal roots and ascend the spinal cord up into the sensory regions of the brain. Again, in spinal cord injury, this connection is severed. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. But this is very hard to do. The spinal cord is quite delicate, and it moves significantly within the bony spinal canal. This could cause damage to the electrode, it could cause damage to tissue, or both. But our electrodes are small and flexible, and our robot is able to insert them deep into tissue, perhaps all the way down into the ventral horn of the spinal cord. And so, we have done just that. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Now, to track movement, it's very common to use motion capture markers like you might see in the production of a movie. These can be placed with a light adhesive, and you can see me placing these on my hand. We're going to use these markers to let us zoom in on movement in the next couple of slides. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's do that. So here's a pig, a happy and healthy pig doing what pigs like to do, which is root around for food and snacks. And as you'll see on the floor, there's a blue square. This is a voluntary engagement zone where the pig places itself, indicating that it's comfortable to receive stimulation. When it's in this zone, we stimulate, and if the pig leaves this zone, we'll stop stimulating. And as before, you can see we're able to track the position of the joints and also stream neural data as well. Okay, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial-temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. Okay, so stimulating the spinal cord is only one piece of the story. You also have to get command signals for the stimulation of the spinal cord. Unfortunately, we have a way to do that. We have the N1 link that you've already heard about placed in motor cortex. How would that work? So we place threads in motor cortex and record spikes. These spikes would be wirelessly transmitted in real time and decoded into patterns of stimulation. Stimulation would then be delivered to the ventral horn of the spinal cord, to the appropriate motor pool for the muscles that we'd like to activate. We then activate those lower motor neurons, which causes the muscles to contract and movement to occur. Now, of course, movement without sensation is actually kind of difficult. Just think about what it would be like to try to move your limbs if they're numb. But we can also get sensory information as well. So the sensory consequences of your movement can be recorded in the dorsal horn of the spinal cord in the form of spikes. For example, here, a feather touching the hand. These spikes can in turn be decoded in real time, sent to patterns of stimulation to either the same N1 device in the brain or perhaps a different one in a sensory area. Stimulation of that part of the brain would cause percepts of touch and proprioception, closing the loop. So putting those two loops together, we have motor intentions decoded from the brain, used to stimulate the spinal cord, causing movement, and then the sensory consequences of those actions being recorded in the spinal cord to stimulate the brain, causing perception. Now, we have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider joining us here at Neuralink. Thank you.